Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Central University of Haryana Department of Physics. Today we are going to discuss about the module discrete symmetries, parity operation and time reversal from the paper Quantum Mechanics 1. Now let us first see what are the main points that we are going to be covering in this module. So, firstly, we would study the basic properties such as unitarity, hermiticity, etc. of the parity operator and the effect of its operation on the observables such as momentum and angular momentum of the system. Then we will define the time reversal operator and study its property of antilinearity. It can be expressed in two parts: one, unitary operator, and two, the operation of the complex conjugation and the effect of parity operation on the wave function and the Hamiltonian of the system. Having discussed the continuous symmetry transformations in the preceding module, we now turn over to some well-known discrete symmetry operations such as space reflection and time reversal. Here we shall learn primarily the basic properties of parity, that is space inversion, and time reversal operators and study the effect of these operators on the wave functions and Hamiltonian of the systems involved. Parity operator. Space inversion or parity is the operation in which a right-handed coordinate system is changed into a left-handed coordinate system. So basically what happens is that under this kind of an operation, if you have a coordinate system in which the three axes are directed along the positive x direction, positive y direction and positive z direction, then after this parity operation is performed, the axis along the positive x direction is changed into an axis along the negative x direction. Similarly, the axis along the positive y direction gets changed to an axis along the negative y direction, and the axis along the positive z direction gets changed into an axis along the negative z direction. So in this manner, what happens is that a right-handed coordinate system gets changed into a left-handed coordinate system. That means that positive x goes to minus x, a plus y coordinate goes to minus y coordinate, and a plus z coordinate gets transformed into a minus z coordinate. And this is a discrete operation which is described by a unitary operator, operator P, which when acting on a single particle wave function gives operator P acting on the wave function psi as a function of position vector r is equal to psi prime as a function of position vector r, and this is equal to psi as a function of position vector minus r. So in this manner one can see that when the parity operator P acts on the wave function psi as a function of position vector r, then that wave function gets transformed into another wave function which is a function of position vector minus r. So if the position vector r had coordinates x, y and z, then the minus r position vector would have coordinates minus x, minus y and minus z. Now this parity operator, when it acts on a many particle wave function, then we get the relation parity operator P acting on the many particle wave function psi as a function of position vector r1, r2 and so on till position vector rn corresponding to the n particles gets transformed to wave function psi as a function of position vector minus r1, minus r2 and so on till minus rn, where now these new position vectors correspond to the same n particles after the transformation. And it is also easy to see that if the same parity operator is operated twice, then we get back the original wave function. So if we take the square of the parity operator, then the answer comes out to be 1, or we can also say that the parity operator P is equal to the inverse of the parity operator. Now, since the operator is Hermitian, where when we say that an operator is Hermitian, it means that the operator and its adjoint are equal, or operator P is equal to operator P dagger. So using the fact that the parity operator or the space inversion operator is Hermitian, and also the property that we have just discussed above, that operator P is equal to operator P inverse, we can write that the adjoint of operator P, that is operator P dagger, is equal to operator P inverse. That is, the parity operator is both Hermitian as well as unitary, because the property that operator P is equal to operator P inverse is the property of an operator to be unitary. And so from this relation, that operator P dagger is equal to operator P inverse, one can say that the eigenvalues of the operator P are either +1 or -1. Properties of parity operator. The two corresponding states referring to the two eigenvalues obtained for the parity operator, that is +1 and -1, refer to as the even states and the odd state. So if the parity operator P acts on a wave function psi plus as a function of position vector r and yields the wave function psi plus as a function of position vector minus r, which turns out to be equal to the original wave function, that is wave function psi plus as a function of position vector r, then the wave function psi plus as a function of position vector r is called an even state. And if the parity operator acting on a wave function psi minus as a function of position vector r yields the wave function psi minus as a function of position vector minus r, and this turns out to be equal to the negative of the original wave function, that is turns out to be equal to minus of psi minus as a function of position vector r, then the wave function psi minus as a function of position vector r is referred to as the odd state. Now it is important to note over here that the wave functions psi plus as a function of position vector r, which is the even state, and psi minus as a function of position vector r, which is the odd state, belong to different eigenvalues and that they are orthogonal. That means that the integral over the entire space, that is integral over the vector dr times the product of the complex conjugate of the wave function psi minus as a function of position vector r and the wave function psi plus as a function of position vector r turns out to be 0, which means that they also form a complete set, because any wave function can be expanded in terms of these two wave functions or as a linear combination of these two wave functions. So we can write a wave function psi as a function of position vector r, which can be written as psi plus as a function of position vector r plus psi minus as a function of position vector r. Now the action of the parity operator P on the observables like the position vector r operator and the momentum vector P operator is parity operator P acting on the position vector r operator times parity operator P dagger is equal to minus of position vector r operator. Similarly, parity operator P acting on momentum vector P operator times parity operator P dagger is equal to minus of the momentum operator P. So from these two examples of the parity operation on the observables, one can state the general form of this operation, which can be written as parity operator P acting on an operator A times parity operator P dagger is equal to minus A operator. And this relation can also be stated as the commutation relation between the operator A and the operator P, and this relation can also be stated as the anti-commutation relation between operator A and operator P, and can be written as operator A times operator P plus operator P times operator A is equal to 0 operator is equal to the anti-commutator between operator A and operator P. Action of parity operator on the Hamiltonian. Now let us discuss that what is the action of the parity operator on the Hamiltonian of the system. In general, if we have any operator A, then the parity operator P acting on operator A, complex conjugate or the adjoint of the operator P is given by minus of the operator A, or in other words we can write operator A acting on the parity operator P plus parity operator P acting on the operator A is equivalent to the anti-commutator of the operator A and the parity operator, and this is equal to 0. That is, the operator A and the parity operator P follow the anti-commutation relation. Then the operator A is odd and the operator A is even if the parity operator P acting on operator A times the parity operator P dagger is equal to the operator A, or the commutation of the operator A and the parity operator P gives a 0. Thus, the operator is even or odd if it commutes or anti-commutes with the parity operator, as illustrated by the example taken above. Thus, the parity operator P is an odd operator, while the orbital angular momentum operator L, defined as orbital angular momentum vector L equal to the cross product of the position vector R operator and the linear momentum vector P operator, is even, which is pseudo or axial vector because both the linear momentum operator P and the position vector operator R change sign under parity operations. Therefore, the orbital angular momentum operator is even function under the parity operation. Now, for example, if the parity operator commutes with the Hamiltonian of the system, the parity is conserved and simultaneous eigenstates of the Hamiltonian and the parity operator can be obtained. So, for a non-relativistic Hamiltonian which has the kinetic energy part with which parity commutes and the potential energy part, it turns out that in the case of strong nuclear forces or in the electromagnetic interaction, parity is conserved, while in weak nuclear interaction through which the process like beta decay or nuclei or decay of nuclei occur do not conserve parity. Time reversal invariance. Time reversal is the operation in which time is reversed, that is, the time t goes to minus t. The observable, such as the position coordinate, is time independent and does not change sign under this operation. Whereas momentum or angular momentum is time dependent and would change sign. Thus, the position operator R is Under the time reversal operator's influence, we can write it as the position operator R is equal to time reversal operator acting on the position vector operator R, time reversal operator dagger, and this gives us the result R. And the momentum vector operator P is equal to the time reversal operator acting on the momentum vector operator P, time reversal operator dagger, and this gives the result of minus the momentum vector operator. Similarly, the orbital angular momentum vector operator L can be written as time reversal operator acting on the orbital angular momentum operator L, time reversal operator dagger is equal to minus of orbital angular momentum operator. So from these three relations, one can see that while R being independent of time reversal is not affected by the time reversal operator, however, the linear momentum operator and the angular momentum operator both, because they depend on the time, change sign under the operation of the time reversal operator. Antilinear property of time reversal operator. Now, these equations provide important information about the nature of time reversal operator. So, if we consider the x component in the first two equations for the time reversal operator, then we get the commutation relation as the commutation relation between time reversal operator acting on the operator x times the inverse of the time reversal operator with the time reversal operator acting on operator px times the time reversal inverse operator, and this commutation relation is equal to the commutation relation between operator x and operator minus px. So one can thus write this equation as time reversal operator acting on the commutator between operator x and operator px times time reversal operator inverse is equal to minus of the commutator between operator x and operator px, and this one can easily see from the previous equation that we have just discussed, that if you substitute that equation in this new equation, then one can obtain this result. And using these two relations, one can thus say that time reversal operator acting on IH cross times time reversal operator inverse is minus of iota times H cross, where iota is the imaginary number minus under root of minus 1 and H cross is H upon 2 pi, where H is the Planck's constant. So in this manner one can see that both iota and H cross are constant numbers, and it shows that the time reversal operator changes a number into its complex conjugate. So if the number is a complex number, then the operation of the time reversal operator on that number simply changes that number into its complex conjugate. And thus, if we have a sum of two such numbers or wave functions, that is alpha times psi 1 plus beta times psi 2, then time reversal operator acting on alpha times psi 1 plus beta times psi 2 gives us complex conjugate of alpha times time reversal operator acting on the wave function psi 1 plus complex conjugate of beta times time reversal operator acting on the wave function psi 2. And in this manner, an operator having this property is said to be antilinear, or in other words, the operator is therefore not a linear operator. Time reversal operator as a product of the operator u times operator k, where u is a unitary operator and k is a reversal operator, or an operator which basically gives us the complex conjugate. So if we look at the property of the time reversal operator, Then we can also study this property and its effect on the time-dependent Schrodinger equation. So if we write the Schrodinger equation as iota times h cross del by del t acting on the wave function psi as a function of position vector r and time t, that is partial derivative of the wave function psi as a function of position vector r and time t with respect to time. This is equal to bracket open minus h cross square by twice m times del square plus v as a function of position vector r bracket close whole acting on the wave function psi as a function of position vector r and time t. Now when we change the time in this time dependent Schrodinger equation from t to minus t, then it yields the equation minus iota times h cross times partial derivative with respect to time of the wave function psi as a function of position vector r and time minus t, and this is equal to bracket open minus h cross square by twice m times del square operator plus potential v as a function of position vector r bracket close whole acting on the wave function psi as a function of position vector r and time minus t. Now if we take the complex conjugate of the above equation, we restore it to its form as iota times h cross times partial derivative with respect to time of the wave function psi star as a function of position vector r and time minus t, that is the complex conjugate of the wave function psi, and this is equal to bracket open minus h cross square by twice m times del square operator plus potential v as a function of position vector r whole bracket close times wave function psi star as a function of position vector r and time minus t. And from this equation one can see that it follows that the wave function psi as a function of position vector r and time t is a solution of the time dependent Schrodinger equation, and so is the wave function psi star as a function of position vector r and time minus t, where psi star is the complex conjugate of the wave function psi. And thus we have seen that an antilinear operator is different from a linear one only in the sense that it provides an extra effect of complex conjugation, as we have seen from the example considered above of the time-dependent Schrodinger equation. Thus, we express time reversal operator as a linear operator u times the complex conjugate operator k. That is, the time reversal operator can be written as a linear operator u times the complex conjugate operator k. Action of time reversal operator on states. Now, after having studied that the time reversal operator is actually a product of the linear operator u times the complex conjugate operator k, we can then see the effect of time reversal operator acting on the wave function psi, and this can be written as time reversal operator acting on the wave function psi as a function of position vector r and time t is equal to the linear operator u acting on the complex conjugate operator k acting on the wave function psi as a function of position vector r and time t, and this turns out to be equal to linear operator u acting on the wave function psi star as a function of position vector r and time t, where psi star is the complex conjugate of the wave function psi. Now we choose to denote the linear part of the time reversal operator by u to indicate that it is a unitary operator, and therefore one can say that the norm of the wave function psi prime, which is given as psi prime is equal to the linear operator u times the complex conjugate operator k acting on the wave function psi, and this norm of the wave function psi prime defined above is ensured to remain the same as that of the wave function psi. That means that the norm of the wave function psi prime, which is basically the wave function psi on which the linear operator and the complex conjugate operator are acting, is the same as the norm of the wave function psi. And in a similar manner, one can also say that the scalar product of two functions phi and psi under time reversal operator, that is under the operation of time reversal, changes to the wave function time reversal operator, as in the scalar product of the time reversal operator acting on the function phi and the time reversal operator acting on the function psi. And this turns out to be equal to the scalar product of the function phi and function psi whole star, that is the complex conjugate of the scalar product of the function phi and the function psi. And this can also be written as the scalar product of the function psi and function phi. That means the order in the scalar product gets reversed. Note that in this case, the matrix element of the operator A, that is, if we are considering an operator A, then if a time reversal operator acts on the operator A, then the matrix elements of this operator A are given as, so we take a scalar product of a function phi and operator A acting on function psi. This is equal to the scalar product of the time reversal operator acting on the function phi and the time reversal operator acting on the operator A times the function psi whole star. That means the complex conjugate of the scalar product of the time reversal operator acting on function phi and the time reversal operator acting on the operator A acting on the function psi. And this can then further be written as the complex conjugate of the scalar product of the time reversal operator acting on the function phi and operator A prime times the time reversal operator acting on the function psi, where operator A prime is given by the relation time reversal operator acting on operator A times the inverse of the time reversal operator. Thus, if the operator is invariant under time reversal, its matrix elements between any two states is equal to the complex conjugate of that between the time reversed states. Time reversal invariance. Now the explicit form of the operator U, that is the linear operator, depends on the system that is under study and on the kind of representation that is being used. So, for example, in the coordinate representation where we have position vector r as real and the momentum vector p as an imaginary quantity, that is position vector r is real and the momentum vector p given by minus iota times h cross times del operator is an imaginary quantity, then the time reversal operator acts as the operator k, that is the complex conjugate operator, and the unitary operator u, which is equal to the unit operator. Whereas if we use the momentum representation in which the momentum vector is real and the position vector is imaginary, that is the position vector is given by minus iota times h cross times del operator p, whereas the del operator is the differentiation with respect to the momentum vector, then here the operator u can't be unity and we get the relation operator u acting on the momentum vector p times operator u inverse is equal to minus of momentum vector p operator. Thus, the time reversal operator acting on the wave function psi as a function of momentum vector p and time t can be written as operator u acting on the complex conjugate of the wave function psi as a function of momentum operator p and time t, and this is equal to complex conjugate of the wave function psi as a function of minus of momentum operator p and time t. In the case of Schrodinger equation, we see that the necessary and sufficient condition for time reversal invariance is that the time reversal operator commutes with the Hamiltonian. Thus, it is now known that the Hamiltonian corresponding to the nuclear weak interaction is not time reversal invariant. And one will get to learn more about this in the modules on nuclear and particle physics. So students, now let us summarize what we have learned in this module. Firstly, after studying this module, you will be able to define the space inversion or the parity operation. Then learn the basic properties such as unitarity and hermiticity, etc. of the parity operator. One can study the effect of its operation on the observables such as momentum and angular momentum of the system, which is something that you've already done. And you can then evaluate the observables such as momentum and angular momentum under the operation of the parity operator for various systems. Similarly, you can also, using the meaning of the invariance of the Hamiltonian of the system under parity operation, use it to evaluate your various systems, and then defining the time reversal operator and study its property of antilinearity. Then you have also got to know that the time reversal operator can be expressed in two parts, that is, it is a unitary operator, and two, the operation of the complex conjugation. So the time reversal operator is basically an operator which has both these operators, that is the unitary operator and the complex conjugation operator. And using this, you can then use it in various applications. And finally, you have learned the effect of its operation on the wave function and the Hamiltonian of the system. Thank you.